I mean, the algorithms and how to define those algorithms, or how to devise those algorithms, as well as we have seen the recursive algorithms, which are nothing but the just like recursive functions, they call themselves. And one of the example, we have taken factorial as an example in the last class and have seen its tracing also, as well as we have seen the tower of Hanoi problem. Now, in today's class, let us try to look at another classical problem of permutation generator. That is nothing but it also represents the how recursive algorithms are devised. Now, in permutation generator, let us take an example. Suppose we have n number of elements. The problem is to print all the possible permutations of that set. So if we have n number of elements as a collection, as a set, we need to print all the possible permutations. Now, to do this, let us take an example. Suppose if we have only one element in a set A. Its permutation is only A. That's only one permutation it has got. Suppose if there are two elements in the set, that is A comma B, then they are two permutations, that is A and B and B and A. In the same way, suppose if we have three elements in the set A, B, C, then we are going to have 8 permutations, that is A, B, C, A, C, B. Now, if you look at this, the set with 3 elements, what we are going to have is, if there is only one element, we have 1 factorial, that is the permutation. We have 2 elements, we have 2 factorial as the answer, that is we have 2 permutations. And if you have 3 elements, it's 3 factorial, which is nothing but 6. Sorry, I told you 8, 6 earlier, it's 6, sorry. So to generate all possible permutations of a set, it's n factorial. So if you have n elements, then all possible permutations will be n factorial. So in this case, if there are 3 elements, then we have 6 elements, or 6 possible, sorry, if you have 3 elements, you have 6 possible permutations of those 3 elements. Now, how is this constructed? Now, if you look at this, the first set, the first element is A, followed by permutations of B and C. That is BC, CB. Then in the next case, next 2 elements is the element B, followed by all permutations of A and C. That is AC and CA. The same way we have the third, third part, that is with third element, we consider third element. Third element, we have C as the element, followed by all permutations of A and B, that is AB and BA. So if you look at this scenario, you can see that this comes like a classical example of permutations. Because if you have 4 elements now, what will happen? Suppose A, B, C, D. What will happen is A, the set of elements will be A, followed by all the permutations of B, C, and D. The same way, B followed by all the permutations of A, C, and D. So if you look at this part, all permutations, when we are saying all permutation of A followed by all permutation of BC, now for BC, we know that how it is computed. It is nothing but B followed by all permutations of C. So this forms a classical, again a classical recursive problem. So to solve this problem, what we have is, we have the algorithm known as perm for permutations. It takes A as the array of possible elements, A, B, C, D. Then K is the number of how many permutations we want. Starting from which element we want the permutations. And N is nothing but the number of elements in the set. So first thing, the base condition for this for generating all the permutations, possible permutation is if n ak equal to n, then simply print the whole array itself, is whatever elements are there. Else, we will have a for loop starting from the first element till the the kth element till the nth element. So if we have two elements, then k will start from 1, next time k will be 2. Then swap these elements, because that is what we are doing. We are trying to actually form the permutations by swiping a, like if we have a and b, the next time it will be b and a. Then again call permutation, that is for the next part, okay, from k plus 1 till n in the same for loop. This is how recursion is done. Then again swap the elements. So when we say a followed by b and c, that means the first element is a, which is going to be as it is, and this b and c is going to be, first time it will be bc with this swap, and then the second time it will be cb. So that is how the permutation is done, or all the possible permutations can be computed for n number of elements. Now, the best way to check this problem or how this works in any programming language, whether it is C, C++, or Python, what we can do is we can start with a. Let's suppose we have 3 or 4 elements. Let's say if we have 4 elements, then call per first by passing 1, 4. Then next time call the perm function with same a, 2, 4, 3, 4, and 4, 4. So then we will come to know about the exact how all the you will be able to find how this thing is working for the permutations problem. So these were some of the examples that we had with respect to recursive algorithms. Now let us come to the core of our base or core of our the design analysis of algorithms, and that is why actually we are trying to do this. Now let us look at, okay, let us now talk about the major thing, which is performance analysis. Now performance analysis, that is the main reason we are trying to learn this subject of design analysis of algorithms. That is where the part of the term analysis comes from. So this is very important part or important topic, where we are going to discuss about which algorithm and how to know that which algorithm is better. Now performance analysis actually, or to judge an algorithm, we actually have some criteria. That is, the first and foremost basic thing is we should know that the algorithm is doing what it is intended to do for. Like when we say factorial is an algorithm, it should compute factorial. When we are saying tower of n, it should compute tower of n. It's not that tower of n is computing factorial. Then does this correctly work? For example, factorial of n. If n is 5, the answer should be 120, not 24. So it should work correctly also for all cases of inputs. And the third thing is, do we know how to use it or how it works? For example, is there any documentation provided? An algorithm will have certain parameters, factorial of n. You should know what n should be. Now, can I give the n value as a floating point number to calculate factorial of 5.5? No, that's not possible. So you should know how it works. Then, is code understandable? or is it readable? For example, I mean, you may use any type of variables, any kind of variables, but is it actually understandable by anyone who can look at it? Now, these criteria, these four criteria are well and good when a software is developed or when a program is written, when an algorithm is devised. But actually, in this, we are not concerned with these criteria in this subject. This is about software engineering. We are concerned, this is not part of design analysis. We are concerned about other criteria which actually affects the performance, or based on those criteria we can judge the performance. That is, first is the space complexity, and the second one is the time complexity of an algorithm. Now, throughout this subject, we will be concentrating not on whether the algorithm works or not. We know that algorithm works. It is devised, it is developed that way, it works. We are not will not be bothered about whether it gives the right result or not. It is definitely going to give the right result or results depending upon the input. We will more be bothered about, or the whole subject is about space and time complexity, and especially about time complexity. So, what actually we are trying to do here in performing the analysis or is nothing but, I mean, or computing which algorithm is better is nothing but we are trying to measure a goodness of an algorithm. Now, to do this, to measure the goodness of algorithm or which algorithm performs better than the other, because for a problem we may have many solutions. An algorithm is nothing but a solution. So, which solution is better? Because there are several solutions to solve a problem. So it's actually we are trying to find the goodness or measure the goodness of an algorithm. Now, for example, I mean, to measure time, we have a stopwatch. For measuring the distance, we have a scale. I mean, scale in the sense, I mean, maybe 10 feet or whatever dimensions we have. The same way for measuring the speed of the car. I mean, we don't take a scale to measure the speed of the car. To do that, we have a separate measuring tool. That is nothing but our what do we call speedometer. And then, for example, to measure blood pressure, we don't use a thermometer or we don't use a scale to measure blood pressure. We have a separate tool for that, to measure a blood pressure. So, like we have different tools to measure uh, the measure different things, and we have different tools or suitable tools to measure. The same way we have to use certain tools to measure an algorithm. Now, the very first thing is, before we move on to which tools we will be using or how which tools are used to measure the algorithms, let us talk about. We said we need to measure the goodness of an algorithm. Now, why do we need to measure the goodness? This is because we need to have some tool or a mechanism to compare algorithms, compare which algorithm is better, which runs faster, which algorithm consumes less space. That is how we will be able to predict its performance. That is, I mean, for certain number of inputs, this algorithm might run faster. Or, I mean, some other case or some other output, another algorithm might run better. I mean, when we are talking about comparing algorithms or predicting performance, we are comparing the same sort of algorithms to solve the same problem. It is not that we will not be comparing a factorial algorithm with a Fibonacci. The Fibonacci algorithm and factorial, there is no comparison because they both do a totally different task. They try to solve a completely different task. So we compare algorithms which solves the same problem. For example, sorting is there, searching is there. Now we have a linear search, we have binary search. So we will be predicting the performance of linear and binary search. We will not be predicting the performance of linear search with merge sort algorithm or selection sort algorithm or bubble sort algorithm, because that's a sorting technique and this is a searching technique. So we predict the performance, or we compare the similar algorithm or algorithms which solve the same problem. So remember, that's the very important point. Then we now want to know how much time and amount of resources are spent when the algorithm runs. So these are the three, broadly speaking, criteria. I mean, we have we perform analysis for. Now, let us come to the formal definition of what the space complexity is. Space complexity is the amount of memory needed to execute an algorithm, or for an algorithm to run to its completion. And the same way, time complexity is the amount of time needed by an algorithm to run to its completion. So remember, the name itself suggests, and both is the amount needed by an algorithm to run to completion, that is, should complete its execution. If space complexity is there, then it is the amount of memory. If time complexity is there, then it is the amount of time needed by an algorithm to complete to its execution, or complete to its what do we call, completion. Now, there are two ways of analyzing the algorithm. One way is the priori estimates, or priori analysis, or priori or theoretical analysis, what we say. Sorry for the disturbance. Actually, I got an important message. Anyway, to measure the performance, what we need is, we have two ways. One is priori estimates, also known as priori analysis or theoretical analysis. Now remember, the term priori means prior to the execution of the actual program or algorithm itself, we can estimate its performance. And remember, it is estimating. We don't have the correct, that we don't say that it runs in 5 seconds or it runs in 2 minutes. It's estimate, priori estimate. The second thing is the posteriori testing or experimental analysis, or sometimes also some textbooks refer to this as posteriori analysis. Now this posteriori, remember, it says testing. Posteriori is nothing but it's post writing of the algorithm. That is, actually, when the algorithm is run on a machine, what will happen? So that is why the term testing is coming here. So when we actually run a program on a machine, how much time it takes, or how much amount resources it takes, or how much amount of I mean, how much amount of time or how much amount of resources it is consumed. Now, through these two things, we actually try to analyze the algorithms. One is priori estimates, and the other one is posteriori testing. Now, there are certain disadvantages in posteriori testing or experimental analysis. And let us first talk about what this posteriori testing or experimental analysis. The posteriori testing is actually a program is run and the runtime of the program is measured. I mean, on giving various inputs. For example, if I have factorial, I give factorial of 1, I say how much time it takes. I give factorial of 5, I say how much time it is taking. I compute that time. Now, computing time is nothing but every programming language actually has a time function or time library. Through that, we can measure the lapse time. That is from we can use what was the time at the starting of the function. I mean, when algorithm is converted into a function, or the starting time of function, and what at the end the function, I mean, exits. What is the time? How much time it has taken? So minusing those two times, we will get how. I mean, what is the amount of lapse time or the amount of time it is taking. Now, when this is done, this kind of measuring technique has certain disadvantages. For example, I cannot measure the time for every input. Now, a factorial of 5, factorial of 6, 7, 800, factorial of 100, factorial of 1000. How much? Where is the end? So I cannot test it on every possible input. And the furthermore is, now I may be running on one system, and you may be running that same algorithm, same code converted to a high-level language. I mean, same algorithm converted into a code of a high-level language on a different machine, on your laptop or on your system. Now, my system might be, I mean, my and your system has different configurations. Your system might be, I mean, a gaming laptop, or your system might be a high-performance system, and my system might be a desktop where several other things are there. I mean, the hardware itself is different. So what happens is, for the same sort of an input, you may be getting a different time, and I may be getting a different time. So this is one of the major problems there with respect to the posterior testing or experimental analysis. Now, let us formally talk about the disadvantages there. The first disadvantage is the limited input. That is, we cannot test it on all possible inputs. The second one is hardware, and the third one is software dependent. That is what I told you. If you run on your system might be having a higher configuration, so it may run faster on your system than on my system. The same algorithm I'm telling you, converted to high-level programming language, same code when we are running. So it is hardware and software dependent. Then it is also operating system dependent, because on my operating system, on my system, I will be maybe having some version of Windows. You may be having a different version of Windows. As well as at that time, we don't know. I mean, not only on two different systems, on the same system itself, I may run at one time, and if I run it at some other time, I may get a different values, because we don't know what are the resources the operating system is using at that time. So these are the disadvantages there. But experiment analysis is much easier than the theoretical analysis. That is one of the advantages. We have talked about disadvantages. The advantage is that the posteriori testing or experiment analysis is easier than the priori estimates or theoretical analysis, because algorithm is same. We just have to add the start time and the statements for start time and statement for end time. Differencing that, we will get the lapse time. So it is easier than the theoretical analysis. But we cannot predict the precise running time. Neither in both. I mean, even in priori estimates also, we cannot predict the precise time, as well as in posteriori also we cannot predict the precise time of the or the running time of precise running time of the algorithm. Now let us talk about the priori estimates or theoretical analysis. In theoretical analysis, we do not perform the testing, or we do not perform the we do not calculate the amount of resources consumed by actually running the program. We do it, or we perform these estimates or priori estimates or theoretical analysis are performed on the description itself of the algorithm. The second is, since it is performed on the description of the algorithm, we don't actually run the algorithm and check. It is independent of hardware and software. That is, we assume that you take any hardware and software, it will consume the same amount of resources. Then it is possible because I mean, it's an estimate, it's possible to say that it works on all possible inputs. So this was basically about performance analysis. The theoretical aspects of performance analysis. Now let us move on to two topics, that is space and time complexity. We will look at the space complexity first, and then we will afterwards we will take up the time complexity. So let's look at the space complexity. As we all know the definition, that it is the amount of memory needed by an algorithm to run to completion or to complete its execution. This is nothing but actually how many bytes are consumed during the execution of the entire algorithm. Now, space complexity, or how much memory needed, depends on the two components, on the following components, two components. One is the fixed part. This fixed part is nothing but it describes, or it consists of the space for the code, because when you are writing number of lines of code, those that code, lines of code, also has to be saved in the memory. So space needed for the code, as well as space needed for simple variables and some of the constants that we define in an algorithm. Now, the simple variables we will come later. We'll see and we'll look at with an example there. So this forms a fixed part. Then there is a variable part. This variable part is nothing but all the referenced variables, as well as the stack of recursion stack. Now, don't get confused here with respect to the recursive algorithms and recursion stack. Recursive algorithms are actually algorithms, but when recursive algorithm runs, a separate memory will be allocated for each call of an algorithm, recursive algorithm, each recursive call. So that recursion stack is nothing but, stack means it stores the what was the value of the variables or parameters at the time when the call is made, and all those things are stored in a stack in the memory. So that is known as recursion stack. Now even here, so in fixed part we have simple variables, and variable part we have referenced variables. Now we will talk about these two things, or discuss about these two type of variables when we actually look at an example in the next slide. Now, using these two components, that is fixed and variable part, we have a formula. SP. S is nothing but space. P, capital P. This one, SP. This S is a space. So space needed, or space complexity, space needed for this problem P is equal to, this is the fixed part. So C is a fixed part, space needed by the fixed part, and space needed by the variable part. Now here we are taking C, means we are saying that this is the fixed part, space needed by the fixed part is constant. It doesn't change. So I mean, the number of lines what you write, it's constant. I mean, it doesn't matter that the space what you're taking with the simple variables are and the space needed for the code, that is treated as constant space. But we are more bothered about the variable part, which is nothing but used with the reference variables and recursion stack that is SP. So it is constant fixed part plus variable part, that is the space needed or the amount of memory needed by constant as well as the variable part. Now, typically, when a program is executed on a machine, we have every high-level programming language has several primitive data types, that is Boolean, byte, character, int, float, log, and term. What we are going to assume is that we're not going to assume that it is, I mean, an integer will be taking 2 bytes or integer will be taking 4 bytes that way. It depends upon programming language to language. We say that these primitive types, we assume that it takes 1 word. So it doesn't matter if integer takes 2 bytes or 4 bytes in other programming language. We consider that it's 1 word. So if it is 2 or if it is 4 also, it doesn't matter because 2 and 4 are again constants. So int and float, if int is taking 2 bytes, float is taking 4 bytes, again, there 2 and 4 are constants, constant values. So we consider that they occupy 1 word. We are assuming this. And then we have, apart from primitive type, we have arrays. That is, we say 1D array, one-dimensional array. One-dimensional array, whether it might be a character array or a float array or int array, doesn't matter. If we considering int, float, everything takes 1 byte or 1 word, sorry. Then if there are n number of elements in the array, it will be taking or occupying space for n number of words. Same way, if we have 2-dimensional array, if we consider 2-dimensional array, then it is a of n by n. So obviously the amount of the number of elements will be n into n words. That is nothing but the amount of memory that will be consumed. So this is what we assume that the primitive data types, whatever data type might, because why we are saying we are assuming 1 word, because in algorithms we do not define type of the variables. The type of the variables, when you convert that algorithm into a high-level language, a programming language, whatever suitable type is needed, we try to use that data type. So here, that is why we are assuming that variables, the variables of primitive type will be taking 1 byte. An array will take n words, that is the number of elements. An array of 2 dimension, that is matrices, will take n into n words. So this is we assume that this is the amount of memory occupied. Now let us come to the practical scenario of looking at an algorithm and trying to find its space complexity. Now, if you look at this algorithm ABC, some name ABC is given. The algorithm, it takes 3 parameters, that is A, B, and C. And the purpose of this algorithm is to compute certain expression. We will not be bothered, we will not bother about what that expression is. It's some A plus B plus B multiplied by C, some kind of an expression it is. Though they should not be an equal to here, sorry. I'll just change, by mistake, it's just actually plus. Got it as equal to, anyway, let us. So this is the expression that has to be evaluated. And the result has to be returned. Now, how many variables we have here? We have parameters. There are no local variables here, actually. We have parameters A, B, and C. So the memory consumed by this is 0 because there are no local variables. And this A, B, C is nothing but they are parameters, they are simple variables which are already defined in the fixed part. Because these are not arrays, or these are not going to be referenced again and again, or these are not going to be referenced by any local variables, these parameters are directly used in the expression. So these parameters will be taking, these are considered simple variables which will be taking a fixed part or amount of memory. So that is why we say that the whole algorithm actually consumes 0 words. Actually, it is not 0 words. It is actually the S of capital P is C plus SP. SP is 0. So C is there, but which is a constant. So we consider that this algorithm takes 0 words because we are not bothered about fixed part. Then let us see another algorithm. This is nothing but it's computing the sum of n number. That is just nothing but arithmetic progression. So here, if you see, look at this whole algorithm. This algorithm, the first we have total as the local variable. So this will occupy 1 word. Then we have another variable I, which is also a local variable. It will occupy 1 word. Then the next thing is, in while loop, I we have already used, it occupies 1 word. We have n, which is nothing but it's a parameter. Now remember, earlier parameter we considered that as a simple variable. But here we were not considering simple variable. This is known as a referenced variable because this parameter is used inside the program, and while loop will again try to check the condition till the condition becomes false. So this is considered as a reference variable, and it will also occupy, we assume that it also occupies 1 word. So 2 local variables, that is total and I, which occupies 1 word. I also occupies 1 word. Then n is the parameter which is going to occupy 1 word. And no other variables are defined. So the total time taken by the variable part is SP is nothing but 3 words, which is also constant, which is also called as constant time. Now let us look at this. Now earlier algorithm, sum of n numbers is we are trying to compute sum of n natural numbers actually. Now this sum is nothing but sum of the elements stored in an array. So sum of elements. So A is an array here, and n is the number of elements in the array. Now even here what we have is we have S as the local variable, which occupies 1 word. Then we have I as a local variable, which is used in for loop, and n is a parameter there, which is number of elements in the array. So these two will occupy 2 words. I is local variable, n is the parameter, so I will occupy 1, n will also occupy 1, which is nothing but 2 words. Then apart from this, we have an array A of I. This array A is an array. So array, we are saying that the number of elements in the array is n. So this array will be taking or occupying, since it's a referenced variable, because we are passing array. Array is actually somewhere in the memory, storing the number of elements. And here, when we say A of I is referencing, we are referencing those elements. So here, what we have is the size or the amount of memory A is going to consume is n words. So there are no other variables, local or parameters. We have considered everything. So the total amount of memory consumed for the variable part is nothing, but we are not bothered about how much is consumed with this code, writing this code of so many lines. That is fixed part constant we are assuming. So don't worry about that, only variable part. So this is SP is nothing but the n plus 3. So we say that n plus 3. So depending upon number of elements in the array, that is if n is 500, then obviously it will be occupying 500 plus 3, that is 3 words or memory spaces it will be consuming. Now let us look at another sum. This sum, was to compute the sum of the elements. This is also sum of the elements, but the elements are not in an array, it is a matrix. So actually here what we are trying to do is we are trying to compute the elements which are stored in a matrix. So A over here in the sum, the parameter A over here is the matrix, N is the number of rows, M is the number of columns. So that is why we have two for loops here, two nested, nested for loop here to compute sum of all the elements of the matrix. So again, for memory for memory consumed, S is a local variable which will going to take one word. Then for loop I is there which takes one word. N is the number of rows as nothing but it's a parameter there. So this occupies two words. And what we have is we have J and we have M. J is a local variable, M is a parameter which also will occupy two words. Then in this expression, S we have already said that it consumes one word. Accessing array is a reference variable. So accessing array, here we have I and J, that is number of rows and columns. So number of rows are N, columns are M. This will be occupying N into M words. So if there is no other local variables and all left. So the total amount of space it occupies is nothing but SP of M N. That is SP of N M or N multiplied by M plus 5. 5 is number of words, 5 words. Now if we consider M and N are equal, then it will be N square plus 5. That is the amount of memory occupied. Then the last thing we will look at in the space complexity is the recursive. The sum we have found sum of n numbers, sum of the elements in the array. That sum function was iterative. The same, problem, that is computing the sum of n numbers in an array. We have is nothing but a recursive function. Now, if you look at this recursive function, the memory consumed will be the recursion stack. First time, our sum recursive sum is called using a comma n. Then next time, if you look at this return statement over here, it is called a of n minus n times. Then it is called a of next time when it works a of n minus 2. Same way till n becomes a 0 equal to 0. So a of 0 it's called. So this is recursive. Recursively it is called from starting from n till 0. So how many times it is called actually? So from n till 0 if you take, it is called n plus 1 times. So this whole thing is called as n plus 1 times. So from n till 0 till the base condition becomes 0, it is going to run the recursive number of recursions will happen will be n plus 1 times. Now in every recursion, this we are going to have n, which is the parameter, that is 1. Then this part a, we will not be having n over here because a is referenced only once, only one will come. So the reference a will be there as well as, so here we have n as 1, then reference variable a as 1. So 2 words are there. Then this whole, the return r sum of a n minus 1 plus a of n, this whole thing is nothing but there should be a memory location to store the result of this operation, so that this operation is returned back. So there are actually one word we need for n, one word we need for a, that is the array reference, and one word we need for storing the result. So there are 3 words actually we need for each recursive call, and there are n plus 1 recursive calls. So n plus 1 recursive calls. That is what n is one word. This whole thing is one. And a, which is the array, is one. So 3 words we need. So every time this recursive call is made, we need 3 words. And n plus 1 times the recursive calls are made. So we have the result as n plus 1 multiplied by 3, which is nothing but the space needed or consumed by this recursive algorithm to compute sum of the elements sum of the elements in the array. So we have SP, that is the space complexity, as 3 multiplied by n plus 1. So this was all about the space complexity. Now let us move on, and last thing for today's session we will look at is the time complexity. Now space complexity was much what did you say, simple. We're just looking at what local variables are, which which variables are coming as the parameters, or which are arrays, or which are 2-dimensional, 1-dimensional arrays. We were able to actually know the amount of resources used. Now, time complexity is little tricky. It's actually the most important thing we are bothered about in this subject in designing analysis of algorithms. Now, time complexity, will first look at the definition, that is just the amount of time needed by an algorithm to complete its execution or to run to completion. Now, time taken by, as the space complexity depends upon several components, that is fixed and variable part. The same way, time taken by program also depends upon following components, that is compile time and running and execution time. Here, compile time, we are not bothered about compile time, because like we treat that as constant, because an algorithm may run once. You may compile once and you may run multiple number of times, or each time you want to run the algorithm, you will compile an algorithm. So it depends upon the language used, and also we don't consider compile time at all. We are only bothered about execution time or running time. Now, before we move further, let us take an example. Assume that we have 2 cars, and both cars have different capabilities. One is a normal car. The other one is a sports car. The lower one, the bottom one, is a sports car. You can, by looking at it, you can say. So assume that it's a sports car. Now, when both cars run from source, they have to go from source to destination. And assume that both the cars are having same number of people. The first car also has 2 people. The sports car also has 2 people. Sitting in the car. Now, when they both move from source to destination, one car may take less time to reach than the other. So let us assume that source car have got better capability. So sports car reaches the source and reaches the destination before the other car. So in the same way, we can say that one algorithm may execute faster than the other algorithm. Now remember that here the problem was same. To go from source to destination, problem is not different for both the cars. Problem is same for both the cars. To move from source to destination. The same way, let us take I mean, the best example of these two things is the searching and sorting algorithms. Now, let us look at another scenario. Assume that now we have both cars of same capability. That is, both are sports cars. Sports cars. Now, here also problem is same. That is, from source, the cars have to move to the destination. But here, let us assume that the first car has two people. I mean, uses 2 persons. Second car has 5 persons. Now here, it is not realistic, but ideally we can say that the car having lesser number of people may reach the destination faster than the car having more number of persons. This may not be realistic, it may not be true in real sense, but ideally if you speak, if 2 persons are in a car and if there's 5 persons, when we compare the weight of the car having 5 persons is more. So, I mean, ideally we say that that car will be taking less amount of time to reach the destination. So here, the purpose of showing this example was to let you know that both the algorithms are same. That is, both cars are same. It has same capability. But one has 2 persons, the other has 5 persons, and one having less number of persons reaching faster. So here, the purpose of showing this is that an algorithm, the size of the input matters, or the inputs, the running time of the algorithm actually is proportional to the size of the input. That is, it increases with the size as the size of the input increases. So even for a same algorithm, when we compare the same algorithm, one with, I mean, the same algorithm at one time with one input and another time with a larger input, the running time will change. That is, it is proportionally, it will increase with the increase in the size of the input. So these was just some of the illustrations. Now let us come to the actual thing of how we do theoretical analysis or a priori estimates on the time, I mean, for the time complexity. There are certain primitive statements, that is, every algorithm will have declaration, which is nothing but in a programming language we declare a total as a variable. So we use int total using in a programming language. So in an algorithm we don't use the data type. So the same way we have assignment statements, for example, total and assigning a value as 0 or I value as 1. Arithmetic operations, computing some expression. Comparison, that is some statements that is with the relational operators, that is less than, greater than, and all, if else if statements. Then accessing elements of the array, for example, a of I, or for a 2-dimensional array, separate thing. Calling functions, and remember this is just calling functions, not defining functions. Calling functions, which is nothing but we use the prototype of the function, that is the name of the function with the prototype, and call the function. And function returning values. Now all these things, function returning values using return keywords. Now all these statements are nothing but considered as primitive statements, and we assume that they will be taking unit time to compute. It will take unit time to compute, that is 1 unit. And this unit is, we don't say it is seconds, minutes, or hours, or days. It's just the unit of time to compute. Now, apart from primitive statements, we also have iterative statements or loops. For example, for loop. Then we have a while loop. We also have repeat until, or what we call it as do while loop. Now, for all these repetitive statements, we say that the amount of time taken depends upon the expression. How the expression is evaluated, or how many times that expression runs, that is how many times that the expression is true, and when does the expression becomes false. So it depends upon that. So iterative statements will take the time depending upon the expression or how the expression is evaluated. But primitive statements, or these statements on the left hand side, will take unit time to compute. Let us take an example. Same example over here also. I have a plus over here. It's not plus, actually not equal to, it is plus. So let us look at this algorithm. We have computed the space complexity of this algorithm. Let us now theoretically compute the time complexity of this algorithm. Here, to compute the time complexity, we count the number of statements, or number of times that statements execute. Now, this return statement, we have talked that it's a returning a value, function returning a value takes unit time. So computing this value and returning is going to take unit time, just one unit of time. That is the frequency of, or the number of times this statement is going to execute. Now the total time is a total frequency of the execution is 1. So we say that in terms of function, in terms of mathematically, as a function, we say that this time complexity is f of n, and this f of n is nothing but it is 1 in this case. And instead of 1, we say c, which is nothing but constant. So c is constant here. So we say that this algorithm is using constant time to compute. Now let us look at this algorithm. We computed the space complexity for this. Let us now try to compute the time complexity. Now this algorithm computes the sum of n natural numbers. So if we look at this stage of the algorithm, or if we compute the frequency of how many times the statements execute, this statement, line 3, it executes only once. That is, frequency of its execution is 1. Then on line 4, this statement is a simple assignment statement. This is also an assignment statement, which is also execute once. Now let us look at this while loop. While the expression we have I less than n. Now suppose this is going to execute for n plus 1 times. Now let us assume that this expression I less than equal to n, we will compute how many times. Let us assume that n is 4. And n is 4, I is 1. So if we have this table, look at this table. Oh, here it should have been 4, sorry. I'll just make a change. Here it should be 4, sorry. So when n is 4, let us look at the table for the expression I less than equal to 4. So when I is 1, the expression is true because 1 is less than equal to 4. Then again I is incremented, so when I becomes 2, the expression is again true. When I becomes 3, again the expression is true. When I becomes 4, again the expression is true. And then finally I becomes 5. Now the expression becomes false. So this expression, if you see, the while loop expression executes for 5 times when n is 4. When n is 4, it's executing 5 times. So when for n times, it will execute for n plus 1 times. That is why we have seen, or we have written the frequency as n plus 1. Then the statements within this while loop is going to execute for n times. Now we have already seen that when n is 4, how many times it is true? 4 times. It is true for 4 times. That is, the expression is true for 4 times. So the statements within the while loop will execute for 4 times. So if it is n, it will execute for n times. The same way, I equal to I plus 1 also will execute for n times. So now, summing up the frequency of, or the number of times this is working, I mean the code is running, or the frequency of number of times the statements execute, we have 1 plus 1 plus 1, which is 3, and n is occurring 3 times. So 3n plus 3. That is total 3n plus 3 times the statements are executed. In terms of function, we can write that the time this function f of n, which is a time function. F of n is going to take 3n plus 3 as the time complexity. Now this 3n plus 3 is nothing but this function. In this case, this algorithm is, we say that it's linear because earlier we had constant, now it's linear because n is linear. N. This expression itself is linear over here, so that is why we are calling it as linear function. Now this, for the same algorithm, I mean what we have computed the space complexity, now we are trying to compute the time complexity. For this algorithm, what we have is, we have we are computing the sum of n elements stored in the array. So the statement on line 3 is going to execute once, so it takes 1 unit of time. This for loop I from 1 to n, so this executes for n plus 1 times. Same way we have seen for a while loop, the same thing here, it will execute for n plus 1 times. Then statement within the while loop is going to execute for n times, because for loop itself is executing for n plus 1 times. So all these statements will execute for n times, and n plus 1th time the for loop becomes false and we come out of the loop. Then return statement is going to take unit time because it's a primitive statement. So here if we compute all the steps, we have the total as 2n plus 3. So this is also a time function, 2n plus 3, and this expression 2n plus 3 is linear, so we call that this algorithm takes linear time. Let us look at another algorithm, add. This add algorithm is nothing but computing the addition of matrices. That is, matrix A is added with matrix B here, and the result is stored in matrix C. So the parameters what A, B, C, what we have is 3 matrices A, B, and C. A, B are 2 matrices which are added, and the result stored in C. And the dimensions of AB are nothing but n and m. N rows, m columns. So this for loop executes for n plus 1 times, because for is going from 1 to n, I is executing from 1 to n. Then the next for loop executes for 1 to m times. But since this is part of the nested for loop of I 1 to n, so jth for loop is executing for m plus 1 times, and since it is in a nested for loop for I, it executes, we have to multiply that with n. So it executes for n into m plus n times. Then we have the statement in line 5, which is actually performing the multiplication. And this, sorry, not multiplication, addition. And this whole statement is going to execute for n into m times. N time is for the for loop, upper for loop, m times is for the inner for loop. So n into m times. So if we sum up the steps or frequency of the, the total number of steps each instruction is using, we have 2nm plus 2n plus 1. So we have a function f of n, time function, what we say 2nm plus 2n plus 1. Now if we assume that n and m are equal, or we consider m equal to n, then we can say that it is 2n square plus n 2n plus 1. And this expression is quadratic because the highest degree of n is 2. So these kind of functions are known as quadratic functions, or taking quadratic time complexity. Now let us look at this multiplication. Now this multiplication, here we have A, B, 2 matrices, and the result is multiplied and the result is stored in C, matrix C. N, M is the dimension for array A, and M and P is the dimension for array, matrix B. So NM is the dimension of matrix A, MP is the the dimensions for matrix B. The result obviously is going to have stored, the dimension of the resultant matrix will be N into P, or N by P. So here we have first for loop is going to execute for N plus 1 times. Second for loop, that is, it's a nested for loop, it's going to execute for N P plus 1 times. P plus 1 is this J for loop itself, and N because multiplied N because it's part of the upper for loop. Then this statement, initialization statement, will run for N into P times. N is for the upper for loop, ith for loop, P is for jth for loop. Then we have K for loop. This is also a nested for loop, but nested, double nested, so it is nested in within I and inside J. So this is going to M plus 1 is for K from 1 to M, and since it is inner for loop to J, it is multiplied by P because J runs for till P, and again J itself is inner for loop for I, it is multiplied by N. So these many times this for loop will execute. Then actual computation part in line 8 will execute for N into M into N. N into P into M times, because M is for this for loop, innermost for loop, P is for the for loop, inner for loop of J, and N is for ith for loop. So if we sum up the frequencies of these, we have 2 npm plus 2 np plus 2 n plus 1. So function, as a function we can write this way, and suppose if we consider n and m is equal to n, then we have the expression as our time function as 2n cube plus 3n square plus 2n plus 1. And since the highest degree of this expression is 3, we say that this is a cubic expression. This is a cubic expression. So let us look at the last example. Now here, if I just have A, B, assume that A and B are two arrays, n is the number of elements, and we are adding these two, summing up. And what I want to do is I want the sum of array A to be stored in sum A variable, and sum of all the elements of array B should be stored in sum B variable. So this is going to take only one. The line 3 is going to take only 1 unit of time. Line 4 is going to take only 1 unit of time. This for loop is going to take this for loop and the below for loop are two different for loops. They are not nested for loops. Remember that. Earlier, what we have seen as the nested for loops. These two are different for loops. So the for loop for I 1 to n is going to take n plus 1 times, and statement inside that will take n times. The next for loop is not the nested for loop, remember. So this is going to take this is going to run individually, which is going to take n plus 1 times, and the statements within this for loop is going to take n times. So if we sum up, we get 4n plus 4, which is nothing but the function, and even this is linear because the n order of n, the highest expression, is nothing but n power 1. So it's linear. So don't assume that if we have two for loops, then it is quadratic, that is n square, expression in terms of n square. If we have 3 for loops, then it is cubic. Don't assume that. Or don't assume that if we have 2 loops, it's quadratic. If we have 3 loops, it's cubic. If they are nested, only then it is quadratic or cubic. If we have 2 for loops, but they are not nested, they run individually, then the algorithm or the number of times it runs is not quadratic. It is simply linear. So it's not based upon what statements we use, whether we use iterative statements or whether we use loops or whether we use primitive statements. It actually depends. time complexity actually depends on number of times those statements executes. It's not on what kind of statements we use. What number of times, it depends upon the number of times those statements executes. So this is what we had. Let us see the last example. Here, this is the first statement. It's going to take 1. This statement is going to take 1 because it's only going to get executed once. Then this statement is going to take once because it's getting executed once. This for loop is going to take n plus 1 times. Statement within the for loop will take n times. And a statement on line 12 is going to take n times because this is also within the for loop. And 30, the line also statements within the for loop, so it's also going to run for n times. Then we print the result, whatever it is. It's going to execute only once. So if this is the computing Fibonacci number, what is the next Fibonacci or the nth Fibonacci number? So if you compute the sum of times this executes, its total is 4n plus 6. That's the number of times these statements are executing. So if we take the function here, if we represent this as a function, it will be 4n plus 6. But 4n plus 6 when? The thing is, we have this Fibonacci for this whole Fibonacci. The first two statements, that is on line 3 and 4, will not execute every time. If n is less than equal to 1, only then these two statements execute. So here we have the representation of that function in a different way. Here we are representing this function as f of n as 2 if n equal to 1 or n is less than equal to 1. And this whole thing will work, the else part will work if n is greater than equal to 1. Sorry, not equal to, greater than 1. So if we say, if we have the compute this thing, we have 1, 2, 3, 4, 4 plus 4n. 4n plus 4 if n is greater than 1. Now, why I have taken this example? Because till now, whatever statements or algorithms we have seen, we did not have any selection part. Run this depending on this condition, else run this. We have seen only loops there. But in such scenarios, such algorithms where we have some conditions within the algorithm, conditional statements within the algorithm itself, and depending upon that condition, the algorithm runs, execute. So we cannot express that just for any value of n. If you take this case, for n equal to 1 or less than equal to 1, we can say it takes constant time, that is 2. And if n is greater than 1, then it takes 2n plus 4 times for execution. So generally we write this as for the function of time complexity as 4n plus 1 plus 4, because we are not bothered of small values of n, we are bothered about large values of n. But actual expression mathematically, if we look at it, this is the way it executes. This is the way it is represented. So even this is linear. Next thing is, last part we will look at is the recursive algorithms, time complexity of recursive algorithms. This time complexity of recursive algorithm, if you look at this statement is going to execute only once. This statement is returning a value, also execute once. This statement is called to a function. But this is not a normal call to a function, it is a recursive call. So when we have this as n, we are calling this function by using n minus 1. So if this whole function takes some function takes, assume that time as t of n, or some function, this whole function takes t of n, then we are passing this n minus 1. So this function, when we call this function, it will take time as t of n minus 1. So if we sum up these things, it's nothing but 2 plus t of time of our sum. This is the name n minus 1. Now we can write this expression as a recurrence relation. Now this recurrence relation to solve, it's not, so if you consider t of R sum as a function, so this total is f of n equal to 2 is 2 from here, which is constant, these two statements, plus f of, instead of t of, we are writing f of n minus 1. These are known as recurrence relations. So if we consider this, t of n will give 2, I mean, take constant time as 2 when n is equal to 0, and t2 plus t of R sum n minus 1 if n greater than 0. So the functions, in terms of functions, we can write it as a recurrence relation as f of n to if n equal to 0, and 2 plus f of n minus 1 when if n is greater than 0. Now this whole thing cannot be directly computed, or we cannot directly say that it's linear, it's quadratic, or it's cubic, the expression, because we don't actually know what this f of n minus 1 will be. We don't actually know what this f of n will be. F of n and f of n minus 1 will be. We have to actually compute them using some of the mathematical models like substitution method or Master's theorem, and get the actual complexity, get the actual time in terms of an expression. So that has to be solved, or what we call as solving or finding the time complexity using recurrence relations. Now, this recurrence relation we will look at and learn in the second unit, I suppose. Yeah, second unit, when we look at divide and conquer approaches. So this I mean expression, what you see here, the whole thing is nothing but it's a recurrence relation, and this recurrence relation is computed using divide and conquer, or solved using divide and conquer approach. So we are going to see how to solve those expressions in the second unit when we go to divide and conquer, that is solving of recurrence relations. So that's all for today. We will continue on the, if you have any doubts or so, just put it in the chat, or you can ask using I mean through the mic or through audio. So if there is no doubts, then we can end this class. Sir, when we are using tsum in this time taken by sir, when we are using tsum, is it the time taken by recursion? Uh, we will actually somebody asked. Yeah. We will actually look at how much time it is taking, or what is the actually before we know the time. We have to find how much, what is its equation, expression, whether it is quadratic, whether it is cubic, whether it is logarithmic, whether it's exponential. So using the recurrence relation, we have to use a substitution. I mean, we have to actually solve the recurrence relation using substitution method. So we will look at that when we solve it. So then we will come to know that how much time it will take. Directly by, because some functions does not reduce. Some functions takes I mean quadratic time to reduce. So uh, it is, we cannot say that it's a time taken by recurrence relation at this moment of time. At this moment, when we solve it, then we will be able to tell that this is the time. This is the quadratic time or cubic time it is going to take. So at this point, we cannot say. So we will solve that recurrence relation, then we will say. Then we will come to understand what it takes. So for timing, just for timing, know that the recursive functions are executed, I mean, solved using recurrence relation. Or time complexity of recursive functions are solved or computed using recurrence relations. Okay, thank you. So anyway, we just log off.